Hi, I'm going to present you epipolar NVS, a method that leverages on epipolar geometry for single-image novel view synthesis. Let's first frame the general scope of our work. From a general perspective, single-image novel view synthesis considers as input a source images and the relative camera transformation that occurred between the source and the target views. It therefore aims to predict a novel view that matches as close as possible the target one. However, the way such camera pose information is fed and encoded to the neural network is often incomplete or suboptimal. Indeed, raw rotation and translation vectors are either embedded into a higher dimensional space or even encoded as one-hot vectors in some cases. Furthermore, the intrinsic K matrices is often discarded, leaving apart the image formation process. Our motivation to design a new camera pose encoding is twice. First, truly account for the geometrical transformation that occurred, and secondly, encode such pose in a way that its representation already contains some strong priors. For instance, by giving some clues on where source pixel should we project on the target image plane. In this way, epipolar geometry allows us to represent such camera pose transformation through a pixel-to-line correspondences as depicted on Figure 2. Regarding our method, we therefore no longer rely on extrinsic or intrinsic camera information. Epipolar geometry defines a fundamental matrix F that takes into account the relative rotation R and the relative translation T, as well as the intrinsic matrix K. Given such a matrix F and any pixel on the source images, we are able to build up a finite set of pixels that defines an epipolar line on the target image plane. A complete pose encoding strategy follows this exact path. By sampling source pixel according to a regular grid, as shown on Figure 4, a complete RGB images is built, representing a relative camera transformation encoding. Such epipolar lines has its RGB color set accordingly to the RGB source pixel color. The complete architecture is shown here on Figure 5. Both the source images and the encoded pose pass through two distinctive convolutional neural networks where the resulting features vectors are concatenated before being fed to the decoder network responsible for predicting the novel view in RGB spaces. Some flow-based hard attention mechanisms are present through the skip connections that exist between the source image encoders and the decoders. We now present some results on 4 different datasets we experienced with. We considered the ShapeNet dataset, a synthetic one where images are rendered on a fixed elevation angle. 2 different classes were used, the chair and cars one. Results on Table 1 highlights how well our method performed by almost always beating current state-of-the-art methods. We also test out our method on 2 real-world datasets called Cynthia and Kitty. While we outperformed concurrent method on Kitty, we managed to get pleasant and competitive results on Cynthia. We present on Figure 6 an instance of all the datasets we get consideration for. While our main concurrent work loosely reproduced the source object size for the 2 classes of ShapeNets, our model truly reasoned about object size and managed to generate sharper and more realistic results. One can have a closer look to the car's wheel or the chair's back. On Kitty and Cynthia, our main concurrent work mostly predicts the source images and fails to capture the relative displacements that occurred in both datasets. While the sign 30 on the ground has disappeared between the source and the target views on the Kitty example, our method successfully captures such drastic change. Let's now have a first focus on an improvement we designed for Cynthia and Kitty datasets. We can observe, as shown on Figure 8, that the car motion across German streets is almost purely translational, with only few turns existing. Such specificity raises a problem with our camera transformation encoding. Indeed, as depicted on Figure 7, and considering the fixed sourced images with 3 consecutive target views, we observe that the 3 encoded pose images are almost the same. This is due to the fact that in such translational motion, epipulse end up in the image center, leading to a similar structure in the encoding. We therefore decided to somehow exploit some depth information by computing the sign distance that was made between the source and the target views along the main car direction. Such delta t value, expressed on equation 1, is finally stored on a 4th channel at the epipolar line's location. Such an additional channel benefit is clearly proved on Table 3, where both mean average error and SSIM scores are significantly improved compared to the original RGB encoding. A similar setting is proposed here, where the source images is fixed. We draw 3 consecutive frames as the target views and ask our model to predict those images with the 3 channels encoding and the 4th one. While the manhole cover that disappears on the target views sequences is entirely discarded with the 3-channel encoding strategy, the extended version we've made managed to grasp the car motion. We finally have a second and last focus regarding an additional loss term we designed, directly inspired from the super resolution issue. On overall, we observed that our generated results were a bit blurry when it comes to deal with tiny and complex structures. High frequencies were somehow lost. We thus decided to add a loss term that will extensively focus on preserving high frequencies components. As expressed on equation 2, low frequency components were obtained through a Gaussian filtering, while our spectral term is thus only based on the high frequencies counterparts. As highlighted on Table 4, adding such spectral terms in our training loss allows our model to better perform at inference time. We highlight on Figures 10 and 11 the positive impacts such a term has on Kitty and ShapeNet datasets. While the white zebra is much sharper on the ground than our concurrent word for Kitty, cars generated on the 3rd column are on overall better synthesized than the one associated with the model that was only trained on the L1 loss function for the ShapeNet cars dataset. In conclusion, our work proposes an innovative way to encode the camera viewpoint transformation by accounting on epipolar geometry for the single image novel view synthesis issue. Thanks to the fundamental matrix F and the different epipolar lines we've computed to get such encoded poses, we truly account for the real physical motion that occurred between the sourced images and the target one. However, our encoding is somehow computationally expensive, since all epipolar lines need to be computed on the fly during training or inferences. We also still need to adjust a bit our encoding strategy with this extended version we've presented on the first focus for the Cynthia and Kitty datasets. Here are the most pertinent work we've leveraged on and compared with. Thanks for your time and your attention.